Hello students, good morning.
Good morning, ma'am.
How are you all? Good?
Yes, madam.
Okay. Do you remember what we have discussed in our previous session? What have we discussed in our previous session? We talked about principle of method of mixtures. Correct? What does this mean? Principle of method of mixtures. When two or more objects or samples of liquids with different temperatures are mixed, then the heat is lost by the hot bodies and the same amount of heat is gained by the cold bodies. That is what principle of method of mixtures is. That means net heat which is lost by hot bodies is equal to net heat gained by the cold bodies. So until when this procedure keeps on going, this flow of heat keeps on going till all these bodies attain thermal equilibrium. Correct? Yes. Using this principle in the previous session, we have found out the temperature of a mixture when two or more samples are mixed or brought into thermal contact. Any questions?
No, madam.
Okay. So let's proceed with the today's topic. So today we are going to discuss about some interesting topic, all right? We are going to learn how to determine the specific heat of a solid. So how are we going to do this? We are going to do this with the help of a laboratory experiment. Okay? So once we understand this experiment and parameters involved in this experiment, then we will be able to determine the specific heat capacity of an object. Okay? So to carry out this experiment, we need calorimeter. What is calorimeter? We'll get to it that in a minute. Okay? And we need some water and we need lead shots. So at the end of the experiment, we are going to find out the specific heat of the lead shots. So what is calorimeter? This is an instrument which is used to make heat measurements, or we measure the temperature using this instrument, this tool. Let's see how this looks. So calorimeter comes with an insulated container. This is an insulated container. What do we mean by insulated container? This container will prevent the escape of heat energy and it will also prevent the flow of heat energy from the surroundings. So it will not gain heat from the surroundings. At the same time, it will prevent the heat to be lost to the surroundings so that we get accurate heat measurements. Okay? And inside this, a stirrer is fixed. Using this, we can mix the solutions inside the calorimeter to, for the heat to get distributed evenly. All right? And a thermometer is fixed. To take the measurements, a thermometer is fixed. So this is our calorimeter. So what we do? We take a calorimeter along with all the equipment like stirrer and the thermometer, and we measure the mass of this calorimeter. So let's say mass of calorimeter is equals to M1. We record this observations. Alright, And then what do? We fill this with water. Okay, now we measure the mass of this entire instrument, calorimeter, along with water. Let's say it is M2, mass of calorimeter with water present in it. Let's say we recorded this to be M2. Now, to get just the mass of water, what do? Mass of calorimeter is M1 and mass of calorimeter plus water is M2. So, if I subtract M1 from M2, I'll be getting mass of water, correct? So, mass of just water is equal to M2 minus M1. Okay. Now, with the help of the thermometer, we take the measurement of the temperature. So, let's say the temperature of water is equals to T1. It is recorded to be some T1. So, the temperature of the calorimeter along with this water is T1 because all these components would be at the same temperature. Water, the container, the stirrer, etc. Okay, clear?
Yes.
Now we need to find the specific heat of lead shots. Let's take few lead shots and we will heat them separately. Let's say we heat them to maybe 100 degrees Celsius or 90 degrees Celsius temperature separately. Alright, how can we do that? By using steam heater or with the help of hot water. Okay, by using a steam heater or hot water, simply we can heat these lead shots. So let's say we have heated these lead shots to a temperature of T2. So lead shots are heated to T2 temperature now. Now what we do is, we take these heated lead shots and we put them in the calorimeter. Okay, give it a while, let the solution settle for a while. What happens? The heat energy flows from the lead shots to the water inside, right? Until the temperature, until these lead shots and water attain a thermal equilibrium and the temperature of this system changes. Yes? So now let's record these measurements. Once we put the lead shots inside the calorimeter, we'll measure the mass again. So now this would be mass of calorimeter with water and along with our lead shots. Let's say this is M3. Okay, let's say it is M3. Now, what is the mass of just the lead shots? Just the lead shots. See, mass of calorimeter and water. Mass of calorimeter and water is M2. So, mass of your lead shots included is M3. So, if I just want mass of lead shots, then it would be M3 minus M2. Correct? Okay. And let the temperature of this entire system after lead shots are put in be, let final temperature be T3. Alright, so we make all these measurements and we record all these observations in our lab book. Is it clear up until this point?
Okay, madam.
Yeah. Now we will go ahead and
Why
see.
only water has to take? Any other liquid also can take, or only water is
Because water is the standard liquid that we find and we know the specific heat capacity of water.
Yes. Okay.
Right? And water is actually convenient to work out this experiment.
Okay.
Alright? We don't want to complicate things too much. So
Okay.
we'll keep it simple, and that's why we take water. Our main objective of the experiment is to find the specific heat of lead shots.
Lead shots.
Okay.
Ah.
So now that we have taken all the recordings, we will see how we can derive the specific heat of the lead shots.
Lead shots.
Okay. Shall we go ahead? Any questions? So now that we have taken all the required recordings, observations, we'll go ahead and derive the specific heat now. All right?
Okay.
Okay. Now, we all know this. We have studied this till the previous session. Heat lost by the hot body in a mixture or when bodies are in thermal contact, heat lost by the hot bodies is equals to heat gained by the cold bodies. Right? So, can I say then heat lost by the lead shots would be absorbed by the calorimeter and water, right? Correct? So, heat lost by lead shots equals heat gained by calorimeter and water. Clear? Now, from the formula of specific heat, we know that S equals Q by M delta T, or in other words, Q equals S M delta T, specific heat, mass and change in the temperature. Alright, now let's say the specific heat of lead is SL. So SL be the specific heat of the lead. Now SC be the specific heat of calorimeter, and in the same way SW is the specific heat of water. So now from this, heat lost by lead equals heat gained by calorimeter and water. You can say Q lost by lead is equal to Q gained by calorimeter and water. Right? Now, from the equation, Q of lead is equals to specific heat of lead, mass of the lead, mass of just lead. What is it? What is it? We have derived it here. See, mass of the lead shots equals M3 minus M2. So, I'll write the same thing, M3 minus M2. And then we have temperature change. Now, how did the temperature for lead shots change? What is the temperature of the lead shots? We heated them to T2 degrees Celsius or Kelvin, whatever. So, the temperature of the lead shots before was T2, and after inserting this in the calorimeter, the temperature falls to T3. So, the change is from T2 to T3. So, this would be T2 minus T3 is the change of temperature for lead shots. Clear up to this point?
Okay.
Now, let's see. Heat gained by calorimeter. Q is equals to Sm delta T. S specific heat of calorimeter, we thought it to be Sc, and then mass. Mass of the calorimeter. What is mass of the calorimeter? M1. Correct? So, I'll take M1 and delta T. Change in the temperature of calorimeter. See, the temperature of the calorimeter was T1. Yeah? Yes, we have written it as temperature of water, but water is present in calorimeter at first. So, for the entire system, the temperature would be T1 only before putting in lead shots. So, from T1, the temperature raised to T3, right? So, change in temperature is T3 minus T1. Why not T1 minus T3? Because T1 is less than T3. So, T1 was the temperature before we have put in very hot lead shots. Once we put in hot lead shots, the temperature would be increased from T1 to T3. So, T3 is greater, and hence it is T3 minus T1. Wonderful. Moving on, water. Heat gained by water. SW, mass. Mass of the water. mass of water equals m2 minus m1. Okay, m2 minus m1 and delta T, change in temperature of the water, same thing, raised from T1 to T3. So it would be T3 minus T1. Now, once we solve this equation, we can find out specific heat of lead. Is this clear up to this point?
Clear.
Okay, let me erase the screen.
Okay.
Now, our aim is to find out the specific heat of lead shots. So, we are interested to find out SL. Fine. So, we will send the other remaining terms on the left hand side of the equation to the right hand side of the equation. Before doing that, can we take anything common from this? Yes. See, T3 minus T1 is the common term. See, T3 minus T1, T3 minus T1. So, we'll take that out as common factor first. Once T3 minus T1 is taken out as common term, we are left with SCM1 here plus SW M2 minus M1. Right? We are interested in specific heat of lead, SL. So, send the remaining terms to the right hand side. So, it would become T3 minus T1 divided by M3 minus M2 T2 minus T3. So we have all these values with us, right? We would be knowing the specific heat capacity of the calorimeter. We know the specific heat of water, and we have measured all these temperatures and masses. So then from this formula, we can find out specific heat of lead. So this is how we determine the specific heat of a solid, by a lab experiment. Any questions?
No, madam.
Okay. We'll move on. So now that we have understood how to determine the specific heat of a solid, we'll move ahead. Okay?
Okay.
So now we are going to discuss about an interesting topic, an interesting process that we observe in everyday life. Okay? That is evaporation. So let us first look at the definition of evaporation. So evaporation is defined as the process of escaping of the molecules from the surface of a liquid at any temperature, right, is evaporation.
Okay.
So before getting into the details, let's think of few examples, alright. We dry our clothes outside in the sun, and after a while what happens, the clothes become dry, right? The water from our clothes disappears.
Okay.
Yes, and also we mop the floor, and sometimes if we want the floor to get dried up quickly, what do? We turn on the fan, right? After some time, what happens? The floor becomes dry. What happens to the water? The water simply disappear.
Okay.
What is happening there? The process which is at play in those situations or circumstances is your evaporation. Okay, to understand this process clearly, let's think of a small experiment. All right, take two petri dishes, okay, and in one and pour few drops of spirit in both these dishes. So we have two dishes and we have drops of spirit in both these dishes. So for one dish, close the lid and keep it aside, and for the other one, do not close the lid, just put it there on the table and turn on the ceiling fan. If you check after a while, what happens? The dish which was kept under the fan, the spirit in that would be disappeared completely. We don't see any spirit there, okay. And in the dish which is kept with its lid closed, few of the spirit will remain, but most of it would be disappeared. What exactly is happening there? How exactly evaporation happens? Let's see. Consider this is the spirit poured in the petri dish, the zoomed in picture of the spirit. Okay, what happens? Every liquid or every object contains molecules in it. Yes, and we know that molecules will have internal energy. Yeah, we have studied about this in the previous session. So all the particles of an object will be constantly moving. They have linear kinetic energy, right? We have thought about this idea wherein we take a box and put in marbles and shake the box. What happens to the marbles? The marbles start moving randomly, correct? That's what happens inside any object. So the particles of an object, the molecules, and in this case, of course, the molecules of the spirit, they keep moving randomly, right, with some velocities. Now, when all the particles inside this liquid drops are moving randomly, they collide with each other, correct? So one particle moving collides with another one. So it's just like how we used to play with our marbles. When we hit one marble with other one, what happens? The second marble will start moving. Yes, same thing happens here also. Once this collision takes place, the energy is transferred from this molecule to this molecule, and now this molecule also will start moving. So this random process keeps happening inside the liquid. Now, once the molecules inside the liquid, once they hit the molecules at the surface of the liquid. Now, the molecules at the surface of the liquid, once hit by the other molecules, they gain energy, right? They gain the energy and they jump out of the surface of the liquid. They come out, right? Now, in other words, these molecules, once hit by the other molecules in the liquid, they gain the kinetic energy. Once this kinetic energy is enough for them, once they gain enough kinetic energy, with the help of this energy, they escape from the surface of the liquid. So this is the random process that keeps happening inside the liquid, right? What happens once any molecule jumps out? Few of these molecules escape and few they collide with the particles of the air. The surrounding air particles would be colliding with these, and few of them might fall back into the liquid. So over the time this process continues, and if the number of molecules leaving the surface of the liquid is greater than the number of molecules returning back to the liquid, then we say the rate of evaporation is higher. This is called as evaporation. So over time these molecules keep escaping from the surface of the liquid. What happens? If enough number of molecules keep escaping from the surface of the liquid, right? Over time, the number of molecules present inside this liquid decreases. The number of molecules keep decreasing, and then the liquid disappears altogether. That means they have evaporated, and hence evaporation is defined as the process of escaping of the molecules from the surface of a liquid at any temperature. Now this process can occur at any temperature is our evaporation. Any questions?
No questions.
Okay.
No.
Okay. Cool. Then the our spirit in the petri dish that we have kept under fan, it evaporates quickly, or on a windy day our clothes get dried up very quickly. So what is this connection between wind and evaporation? Why is rate of evaporation higher when there is wind? So let's see what happens. If this is put under a ceiling fan, the wind will be constantly sweeping away over the surface, right? The wind would be constantly blowing over the surface. Now, the molecules that are escaping from the surface are swept away by this wind immediately, preventing these molecules to return back to the surface of the liquid. So right, so the escaping molecules are blown away from the surface of the liquid due to wind. So that means the chances of these escaping molecules returning back to the surface of the liquid, these chances are slim because there is wind, and hence evaporation is faster under the ceiling fan, or when during a windy day evaporation is faster. Any questions? So now from whatever we have learned, can I say that then evaporation is a surface phenomenon, right? Yes, because it is the process which is occurring on the surface. So evaporation is surface phenomenon. And have you ever observed this when you wash your hands without wiping your hands? If you put your hands under fan, what happens after a while, once all the water is evaporated, you feel colder, right? Why is that? Why is that? We have already learned that the escaping molecules gain energy from inside the liquid, right? And then they move out. That means the energy of the molecules inside is transferred to the molecules at the surface, and these molecules jump out. So from this molecule, energy is transferred to this. Now this molecule takes energy and it leaves the liquid. So that means energy is being pulled out from the liquid by the escaping molecules. So that means when evaporation takes place, energy is being taken out. Once energy is taken out, that means there is not enough heat there, right? Heat energy is being pulled out. That means the system becomes colder, and hence evaporation is a cooling process. Any questions?
No.
So that is about your evaporation. So what did we learn in today's class? We have learned how to determine the specific heat of a solid by a lab experiment, by performing a lab experiment, right? And then we have discussed about an interesting phenomenon, which is evaporation. Okay, done? All right. In the next session, we'll be discussing about few more interesting topics like this. Come back in the next session to find out more. Thank you.